Hi, my name is Mark Stiles, and today I'm going to be discussing the final project for IST 691, Deep Learning in Practice. My teammates were Sean Deary and Devin Hughes. The dataset we worked on was with U.S. municipal census data from the Census Business Builder website. We chose this dataset because we saw a problem. Many local municipalities have lots of data, but not necessarily the tools to guide decision-making. And even when they do, they don't always understand it in context. This project was a way to demonstrate how we can help public leaders make better decisions in a world of big data by using sophisticated tools to predict how demographic and policy changes will affect the outcomes of complex relationships in city and local economies. The dataset we used was built by combining federal government geocodes for cities and looking up those locations on the Census Business Builder website that collects and aggregates data on demographics, socioeconomics, businesses, housing, building permits, and consumer spending. The pages were scraped and saved to files, and the files were mined for the tabular data, which was compiled into a spreadsheet. The result was a 300 variable and over 10,000 row dataset. After cleaning up the data and removing variables that were sparse, categorical, or aggregated, meaning they were not independent, we ended up with 9,653 locations and 173 variables. 54 of those were statistically correlated to the target variable, which was the city revenue. We didn't necessarily eliminate all the others. We did still find that there could be complex relationships between them, and so we left them into the data set that we used for the model. The goal here was to predict the revenue and allow any given city to change these metrics to expected values in the future and see what that might do to the revenue and what additional adjustments local leaders could make to prevent budget shortfalls or even optimize their revenue for the upcoming year. When looking at the initial distribution, we saw there was a long tail. This did end up causing an issue with the training later, and we ended up having to remove the top 54 cities with the highest revenue. Their scale was so outsized that they prevented convergence to an acceptable range. These two graphs show what that change looked like to the distribution. Additional work was done to the dataset to prepare it for training. We first filled in any remaining null values and zeros and converted the state values to a one-hot encoding. There was also where we removed many of the variables and outliers mentioned earlier. The next area we worked on was the test-train split. And to maintain thoughtful independence of the training set and the test set, we set aside a quarter of the data to be used for validation of the models. Since our data set contained variables with numerous ranges, we tried both the min-max and the standard scaler, but we found that the standard scaler really was best fit for our data set. One of the most challenging parts of this project was identifying a good model structure that could both learn the data well, but also allow us to retrain quickly enough while we changed the parameters in data set. After an enlightening class session, we restarted our search with a very simple model and a 2-layer 10-neuron network using a batch size of 200, a standard scaler, and a default weight initialization. We did try different weight initialization settings, but the default was also the most consistent. As we scaled up to 100 and 1,000 neurons, and then again with additional layers, we discovered there was a modest learning increase at each level, but a significant time increase at 1,000 neurons. This led us to use a 100 neuron layer model. The next phase of our exploration led us to using most of the same settings, but increasing the depth of the model. So again, find a reasonable training time with optimal layer count. We found that larger networks with more complex layouts didn't meaningfully decrease the loss more than a 6-layer, 100 neuron network. And in the last phase, we increased the batch size, but we tried the same model for all the training runs except for the last test. Using a larger batch size was a decision we made resulting from a community presentation on a tool called Weight Watchers, which indicated that a larger batch size could improve the weight training. We then steadily increased the number of epochs and found that with a sufficient number, we could attain a loss value that was within a percentage of error of the target value. We also attempted a model where all the layers selected neuron counts were randomly from within a range around 100. But that didn't really seem to improve the training time, so we discarded it. This resulted in the final model. And we ended up using the 6-layer model with 100 neurons and the atom optimizer. We tried 3 different optimizers, including AdaGrad and RMS Prop, but the atom optimizer was the most performant. We also found that a learning rate of 0.001 was a good fit. When training the model, we kept track of the best model, the best loss, and the loss history. This allowed us to see what was happening throughout the training and identify when the loss deviated from the validation. During many of our iterations, we had divergent graphs, but eventually we found a right combination of parameters to train reliably. To track our progress, we use the town I'm from as an arbitrary output metric to demonstrate the actual revenue versus the predicted revenue and the difference between them. It wasn't initially obvious to us, but our best loss, which was 5.34 e to the 5th, meant that we could be off by as much as $500,000. And being such a large number, we initially thought we were really far off from our goal, but visualizing these values put that number into perspective, and we realized that we were often within a single percentage of difference. And given that our target value of city revenue, which could be in a range of hundreds of thousands to hundreds of millions, meant that an error rate of tens of thousands could be an acceptable level. It's also worth noting that the units we're referencing are in thousands, which means that a reference to $7 million is actually $7 billion. We account for this conversion later at the end during the application phase, just to make it clear to the end user. After we were finished training, we loaded the best model, and then we saved it along with the scalar to a file so that we can then use it in an API for a web application. At this point, I want to break out of the presentation and demonstrate the value of the model, however imperfect, and how we could potentially make decision makers understand their local economies better. This web application is using Flask, which is a Python web application framework. The model and scalar were saved to the file they were used in this project. I'll provide a link to all the source code and everything. The application is itself not part of the project. It's really just to demonstrate the bigger vision of what we were trying to accomplish. So this is the census data predictor. And the first field here really lets you look up a name, goes into the data set. If I were to select the location like the city I'm from, it auto selects the first one. If you were having any other names of the similar location, it would list them and you could select them. It's going to list here the fields that you can modify. Not all of them are available. There are over 100, and I didn't feel that was helpful to this demonstration. So I wanted to use just a smaller set that I thought were targeted and really demonstrated what we were trying to get across. On the right side here, as you load a location, it's going to provide you the baseline revenue, which is the actual revenue, what the model predicts it using the actual values. The difference between those two and what that is a percentage. As you go and you make changes to these values, it's going to update this adjusted revenue. And so this adjusted revenue here is within respect to this predicted. And so you're going to see the difference that you're doing as you're making these changes. And so, for example, if I was expecting a massive influx of people into the city, what would that do to my revenue? It's going to put a huge hole. Like, it's not huge as a percentage. It's not, but a $20 million shortfall in the budget. So, just to demonstrate that that's what you're seeing here is this connection. And there could be a lot of reasons why, having a population increase while you don't increase any of the jobs or the housing could have a negative impact on revenue. But let's select the location. I've never been to Boise, but let's imagine I'm a local leader from a town in a place, Idaho. Maybe I have some information about, I'm on the city council. Maybe I know a lot about what's happening in the city. I know generally we've been targeting a population growth that's moderate, but maybe still, healthy. Maybe we're expecting the median age to go down slightly, the average income to go up with inflation possibly. Maybe we're also building new housing. We have some projects underway. We're working on lowering the poverty rate. We know there's been modest increases in food service, new contracts that we're aware of. Maybe we're targeting new education programs specifically, or we've enticed businesses or built a new business park, and we're expecting an influx of new jobs in finance, maybe some in information and technology, maybe an increase in some modest increase in the real estate. Even maybe we had targeted a tax or a tax break to help homeowners with their monthly costs, and we wanted to potentially lower this down. Maybe we understand that rents have been steadily climbing. And so now as a local leader, I can use this tool. I can go in here and I can say, okay, this is what we're expecting. What's that going to do? Oh, okay. Modest growth in a number of different sectors. I'm expecting growth, and I am, and I can actually put some dollar value, within a certain percentage of, accuracy. And I can say, there's likely to get $2 million increase. If I'm putting together a policy that's trying to entice these businesses or this business park, I can start to say, was that policy worth it? Did the money that we invest, is that going to come back to us? Are we going to make that money back? Is it a big loss or not? And now I'm making better decisions. Part of the motivation for doing this was that I had seen an article where during the pandemic, cities were trying to entice people to move to their cities. They were paying them to move. You don't tie to where you work. You can come and live in this other city where we have plenty of space. The cost of living is lower. We'll pay you to move here. They're expecting that value's growth. But in one of the articles I read, the reporter was asking the local official, what data are you using to guide you in this? And they said none. We don't have anything. We just hope it'll work. And so to me, that felt like a gap. You should be using data to make better decisions. It really should be a relationship between what and the politicians, so that you have a really good sense of what you're doing to affect the positive outcome in your local economy. And so that's really the vision and the goal of this tool, is to be able to provide that to those leaders. So jumping back in, so this is the URL for the GitHub account where all the code is. This is where all the Jupyter notebooks that build the data set, that train the model, the web application code. I'm not necessarily open sourcing all of it, but it is open. You can review it. It's here to use it and look at and confirm that it does work. Okay, so this kind of gets us to the looking backwards a little bit now that we're past the application itself. What we were able to build and some of the struggle we had with training, we did consider that using an embedding layer for states could have improved learning and made that model reasonably more accurate. We also think having more time to tune the data sets could have produced better results. We're not certain we eliminated all of the dependent variables or that there weren't more valuable variables that could have been added. There were a lot of sparse data values that we may have been able to use with a different type of network structure or training regimen that we just didn't have time to explore. We also wanted to find ways to eventually reincorporate the outliers. We didn't feel like it was an accurate representation without them, but we did struggle to train this model with them included, so we wanted to get them back in eventually. We did want to be able to convert this model to a Keras model to be able to take advantage of some of the optimized training utilities online and other auto-tuning tools that were available. One of the key things that we really found that would have been valuable was being able to take in the lat long. And we did have it available, we just weren't able to, we didn't have the time to really incorporate it. But there is a pretty high likelihood that the locales that are near each other and they share services have a special relationship, and they either help or potentially even hurt economies near it. And we believe having that value in there really would have improved the overall training of the model. And going through, just the big picture, a lot of the insights that we saw and got out of this exploration was that the business and the housing data really provide a lot of levers of influence for community leaders. This could help tailor policies and optimize the economic benefits to a community. And eventually, municipalities who can optimize their economies will, and they'll have an advantage over those who can't. And we do understand it's not a simple problem. It's not going to be solved by an early prototype neural network. We know how complex an economy is and how hard it is to model it accurately. But making these small advances and proving value may open up other opportunities like data sharing or standardization across communities. That itself could lead to other powerful benefits. And so in closing, I want to leave with this quote. I felt it was in the spirit of what we were trying to accomplish, which was to help local leaders feel confident in the decisions they were making based on good data analysis and not just instinct or luck. But it's never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it is the only thing that ever has. So here's a list of references that we did use to develop the model. Put them on the last slide here. But that's the end of the presentation. So thank you for your time, and I hope you enjoy it.